Technology and scientific advancements form a self-reinforcing system. As technology advances, so does our understanding in science, and with greater understanding, better technologies can be created. It's a mutually inductive process. In this video, we'll have a look at a technology which has had a profound effect on the subject of particle physics. The Large Hadron Collider is, to this date, the largest investment made to human curiosity and the understanding of the universe and elementary particles. This $3.74 billion complex was made purely for two central purposes. The first, to prove the existence of the standard model Higgs boson, and the second is to find a large family of new particles that are predicted to exist by the theory of supersymmetry. The main collider at the LHC consists of a 27-kilometer ring made up almost entirely of superconducting magnets, which form the accelerating structures to boost the energy of particles and increase their speed to almost the speed of light. There are also electromagnets responsible for guiding the particle beams, which are usually proton beams, and are built from superconducting coils. Superconducting coils are essentially lengths of wire or coil which have a resistance that's as close to zero as possible, but this isn't yet possible to achieve at room temperature. Although physicists at the University of Rochester have found a functional close to room temperature superconducting substance, it's far too expensive to mass manufacture and requires pressures of up to 39 million psi. So the entire main collider at the LHC has to be cooled using liquid helium, so that these coils are at temperatures of around negative 271.3 Celsius or 2 kelvins. In total, the colliders require magnets which accelerate and focus particle beams, as well as to squeeze the beams in order to increase the chances of collision. So with all this technology, how close have we come to actually fulfilling the motives laid out by CERN when the LHC was developed? Well, the answer is very, very close and also very far. Let me elaborate. The LHC was developed to prove the existence of the Higgs boson, which it has somewhat done. And we need to understand what the Higgs boson is before I go any further. At school, over most years, we're taught that the atom consists of three main parts: the proton, electron, and neutron. However, this is incomplete. The nucleons themselves are made up of smaller particles. These particles are what make up the standard model, which we were talking about earlier. The standard model itself contains three main categories: quarks, leptons, and bosons. Putting this into practice, for example, a proton is actually made up of two up quarks and one down quark, which are held together by gluons. So with all that, if all these subatomic particles were just charges, then where does their mass come from? And if they were massless, an electron would never remain attached to the nucleus, and all atoms would break down. As well as that, they would just move away from each other. The whole universe would simply collapse. So there has to be something that gives these particles mass. For a long time, this missing piece baffled scientists until Peter Higgs developed a theory of the existence of something that gives particles their mass. However, we lacked the technology to actually verify his theory, and so it remained exactly that. So what exactly was this theory? Well, his theory proposed that the mass that particles had was due to a field, a Higgs field, not the Higgs boson. To understand this field, think about a large pool of water. When someone like a human tries to walk through the water, they're slowed down and they interact with the field. This interaction gives the human their mass, while something like a very fast fish, for example, goes straight through it as if the water was never there. And this is analogous to photons or quanta of light, as they don't interact with the Higgs field, while other particles like electrons do. So that's the Higgs field, but what's a Higgs boson then? Well, the Higgs boson is a particle that can be produced when the field is subjected to very high energy. Colliding proton beams at the speed of light has the ability to produce this energy, and that's where the LHC was born from. It became the medium to proving Peter's theory about the existence of the Higgs boson. Through preliminary runs at the LHC, the existence of the Higgs was never proven, and that's because the Higgs itself is very unstable and decays almost instantly. So fine-tuning the LHC is what essentially made the defining difference. In 2012, the first signature of its existence was discovered in both the CMS and ATLAS detectors of the LHC. This is how it played out. Particle beams left the main particle generator, were accelerated by two circular accelerators followed by a linear accelerator, and finally the main accelerator where they collided. The detectors picked up signatures of the fragmentation of particles that collided, in which was the signature of the Higgs boson, which had immediately decayed. This was groundbreaking discovery. The problem is, physicists at CERN are still unsure whether or not they have found the Higgs boson. The reason being, the signature of the Higgs boson was definitively large, but was not exactly the same as its predicted value. So the question is, have physicists discovered a new family of particles, Higgs particles, in which case the standard model will need major revisions, or have they discovered the standard model Higgs? Well, to answer that, the technology science mutually inductive cycle has continued. On the 30th of March 2021, CERN released an article stating that they're doing major upgrades to their detectors, which will allow them to detect other properties that are predicted by the standard model Higgs, to prove whether it's the standard model Higgs or a new type of particle entirely. The property they will be trying to detect is self-coupling of the Higgs boson. The proof or disproof of Higgs' theory will inevitably further lead to technological advancements as a self-reinforcing process.